what if you keep zooming in? I mean, I guess what happens if you keep zooming in? You get what I mean? And it's a video from veritasium. Bro, I really like their videos honestly, because I don't know, they make cool videos for real. And this shit got 10 million goddamn views, brother. But yeah, let's see what happens if you keep zooming in.
It's a tiny piece of metal just 3 millimeters across. And here's what happens if you just keep zooming in. 1,000 times, 100,000 times, 50 million times. Each of these blobs is an actual atom. I saw this the other day at the University of Sydney, and it kind of blew my mind.
University of
because
Sydney.
Up until just 30 years ago, directly seeing atoms like this was thought to be impossible.
True.
The rooms that you're going to see here are perhaps the most shielded rooms on campus, or even in the whole of Sydney, I would say, and perhaps also the most expensive.
Oh.
That's wild.
So why is it so hard to see atoms?
Well, you can't
Yeah, I was
actually
gonna
see
say,
atoms
if you
with
keep
visible
zooming
light.
in, you're gonna
That's
see the
because
atoms,
while light
right?
has wavelengths between 380 and 750 nanometers, an atom is still over 3,000 times smaller, just 0.1 nanometers. And if the wavelength of light is much bigger than the thing you're trying to see, the light will just diffract or bend around it, so you won't be able to see it.
So if you want to see atoms, you need something with a much, much smaller wavelength. The best candidate isn't even light. It's electrons. In 1924, a French physicist named Louis de Broglie worked out that everything was sort of wave-like. Not just light, but matter too. Atoms, molecules, even you yourself have a wavelength.
And the formula for this wavelength is Planck's
Nah,
constant
dude, this is
divided
out of
by
my-
the object's momentum.
These
that is
formulas
mass
are-
times velocity.
Are
So
too
here
much.
what you actually see, that's the column of the microscope where we accelerate the 300 keV electrons down.
300 kilovolts.
That's the
these
thing.
Electrons.
Yes. So they are relativistic particles.
How fast are they moving? 99% the speed of light, or
Well, around 80.
80%
Wow.
the speed of light?
Yes.
So what would be their wavelength?
The wavelength is the Planck constant over the momentum, right? So if we calculate that, we come to around between 2 to 3 picometers.
Whoa!
Yeah.
That's
I don't
over
know.
100,000 times smaller than
2 to
visible
3.
light. So theoretically, you get 100,000 times.
Visible light is 380,000 to 750,000 picometer, and electron is 2 to 3 picometer. Damn.
Times more resolution. Shortly after de Broglie's discovery, a group of scientists in Germany started working on a microscope that would use these high-speed electrons.
The only problem is you can't bend electrons using glass lenses. So how do you focus them?
Hans Busch, a German physicist, suggested that an electromagnetic lens might do the trick. He published his results in 1926, but never actually built one.
Oh, so who
Fortunately,
built
a
it?
copy of his paper fell into the hands of an eager
I
young
knew it.
PhD student, Ernst Ruska. Ruska built his first prototype by coiling up some wire and surrounding it with iron, taking care to leave a gap in the middle. Then, when he passed a current through the coil, it induced a donut-shaped magnetic field through the metal and across this gap. This was his lens. To test it, Ruska first boiled electrons off a tungsten filament, the same kind of filament you'd find in an incandescent light bulb.
Okay.
He accelerated these free electrons through a positively charged anode down to his electromagnetic lens. As an electron approaches the lens, the magnetic field exerts a force on it. So if an electron is traveling in the y direction and the magnetic fields are in the x direction, this force, called the Lorentz force, pushes it in the z direction. But as the electron moves this way, it encounters other magnetic field lines along the donut shape, which constantly point its motion in a circle. But then this circular motion means the Lorentz force starts pushing the electron inwards as well, spiraling
True.
it
I
into
can
the
see that
center of the
happening.
lens. Now, if you trace the path of the whole beam of electrons, you'll see they all get steered into the center, focusing the beam.
And you see
By
veritasium.
1931, Ruska and his colleague Max Knoll used this kind of design to build the first working electron microscope. It was pretty basic, made of brass roughly bolted together. But it worked.
Okay. If it
The
works,
image
it works.
itself
you
was
know?
created once the focused electron beam hit a sample sitting at the focal point.
Uh-huh.
Sample needed to be incredibly thin, only around 100 nanometers thick. More
Okay.
electrons would make it through the thinner parts of the sample than the thicker parts, creating an electron imprint of the sample. Then a second electromagnetic lens magnified this imprint down onto a fluorescent detector, producing the final image. This was known as a transmission electron microscope, or TEM. Now, early versions of the microscope barely magnified at all. In fact, it wasn't even better than an optical microscope. But Ruska was determined.
He was
Over the next
locked
few
in,
years,
huh?
he experimented with adding more lenses onto the microscope to create bigger and bigger images. By the mid-1930s, Ruska had gotten the TEM way past 10,000 times magnification. It could produce close-ups of insects, bacteria, and even viruses at a level far surpassing the optical microscope. But right as Ruska's TEM was taking off, a German physicist named Otto Scherzer published a paper claiming that the microscope was about to hit a brick wall.
So there's no like future of it.
There was a flaw in the electromagnetic lens, he wrote, that was completely unavoidable. For an electron to make it to the focus of the lens, it needs to be deflected by a specific amount. If you simplify its trajectory, you can define that ideal deflection with this angle theta. This angle depends on the horizontal distance of the electron from the optical axis, and how far down the
this is
axis
so
the
much
focus
math.
is, also known as the focal length.
I hate math.
The shorter the focal length, the stronger the magnification. If you graph this angle as a function of distance to the optical axis, you'll see that it can be approximated as linear. The problem is that the magnetic field doesn't scale linearly. It's much stronger near the edges of the magnet. So if you plot the curve for the actual deflection of the electrons, you'll see that the magnetic field over-deflects the electrons further out. Their angles are bigger than they should be, so they end up focusing before the rays in the middle. And as a result, the focus is spread across the optical axis instead of being contained in a single point.
Okay.
The blur starts out around the edges of the image, but it gets worse the higher the magnification. This is called spherical aberration, and it distorts every radially symmetric magnetic lens.
In fact, it doesn't just affect magnetic lenses.
Every spherical lens, from a camera to a telescope to a magnifying glass, also suffers from it.
But there is a surprisingly simple way to minimize spherical aberration. Just add a second lens, one that diverges light instead of converging it.
Now, a diverging lens also suffers from spherical aberration, but if it has the same amount of aberration as your converging lens, just in reverse, you can stack the two to essentially cancel out their effects, and that removes the aberrations almost entirely. Almost all modern lens systems in cameras and microscopes use some sort of correcting divergent lens.
So you might imagine that the TEM simply needs its own version of a diverging spherical lens to magnify further. But with magnets, this is physically impossible.
Every magnet has two poles, a north and a south.
Right.
It's impossible to just have one. Even if you split a magnet down the middle, it creates two smaller magnets, both with a north and a south. And all magnetic field lines have to start at one pole and end at the other, forming a closed loop.
Is a direct result of the second Maxwell equation, because the field that you
Why I feel like I have seen this guy somewhere else, like in, I don't know, in movie or in some other video, or I don't know if I don't know.
create
I cannot
has
remember.
field lines
He
that
looks
start
familiar.
and end at the same magnet. So the electrons will always cross through two lines. The first time it passes through by the Lorentz force, it's brought into the spiraling motion, and then the second time, from that spiraling motion, which has then a slightly different direction, it's pushed towards the axis. That's why all electromagnetic lenses by default will converge the beam and never diverge it.
Even if you shot electrons in from the other side of the lens, they would still get focused.
The same thing.
This is what Otto Scherzer's paper proved in 1936, stopping progress on the TEM. It is impossible to produce a radially symmetric magnetic lens that diverges.
And this was, of course, a big roadblock for the development of electron microscopy, because people saw, okay, we can accelerate electrons as much as we want. The presence of the spherical aberration will always be in the way.
Because of this roadblock, advancements in the microscope's resolution slowed significantly. By 1955, another microscope beat the TEM to the punch and took the first generally accepted image of atoms. This was
That's
called
the
the
first
field
image
ion
of
microscope,
atoms, huh?
and it worked by shooting helium or neon atoms at an atomically sharp needle tip. The tip was positively charged, so when the gas atoms hit the needle, they
All
got
of them.
ionized and were ejected off perpendicular to the surface. And that could form an impression of the atomic structure of the tip. But this method was limited. You could only get a sense of the atomic structure of the very tip of the needle, and the images weren't all that impressive. Luckily, Ruska's electron microscope wouldn't stay stuck in the realm of insects and bacteria forever. Despite Scherzer's aberration limit, work on the transmission electron microscope continued. During the next 4 decades, people tried boosting the resolution with clever workarounds, and perhaps none more so than
I wanna
British
see the
American physicist
latest
Albert
version, you know?
Crewe. His idea
What we
was
got
to
now?
replace the tungsten filament, which fired off electrons at random, with a more
Okay.
directed source. So instead of boiling electrons off the surface, he tried pulling them off with a stronger electric field. And by sharpening the tungsten into a fine tip, he was able to create a narrow beam which was over 1,000 times brighter than before.
He paired his new narrow beam with an unlikely technology.
You know what I also have noticed about Veritasium team, or especially this guy, or the shot when he's talking like this. Before, if you watch the videos, I don't know, he will go back out again, but before if you watch the videos, he always shoot this kind of shot outside. But recently I'm seeing the bro came in. Bro was like, I'm done outside, maybe it's too cold, you know?
The cathode ray tube TV. These TVs worked by scanning an electron beam across a screen. The screen was coated in a phosphor that produced light when hit by electrons. And by varying the intensity of the electron beam, you could vary the brightness of the screen, giving you a black and white image.
Where is this guy, right? How long he is, like, I'm sure this is his, like, young video picture or something. How long this guy making videos for, man?
Crewe was inspired to design a similar electron beam for the TEM that would scan across the nanoscopic sample. So instead of creating an imprint of the whole sample at once, Crewe's electron beam made smaller imprints, mapping the sample out bit by bit. This wasn't the first time someone had tried to make a scanning version of the TEM.
Okay.
German researcher Manfred von Arden built an early prototype in the 1930s. But it was destroyed during World War II.
Damn it.
When Crewe revived
Alvar.
Arden's design, he made several drastic improvements, and by 1970, he had this, the first image of single atoms taken with the electron microscope.
Again, so before it was first picture of atoms taken. And now here comes a new guy showing another picture of first picture taken of atoms.
This, the first image of single atoms taken
So these are like single atoms, and that was just atoms?
with the electron microscope.
Okay.
Researchers quickly jumped to employ his tech, producing countless images of atoms. After nearly a century of improvements from Ruska, Crewe, and many others, the magnification
Ruska.
upgrades on the TEM had reached their peak. But Scherzer's problem persisted. Spherical aberrations set a hard limit on how small you could see. Even Crewe himself gave up on trying to get around it after over
Bro, what are these guys trying to take out of atoms, man? What are they trying to see here? Like, how deep do they wanna go, you know?
10 years of work. Unfortunately, we could never make it work. After many heartbreaking attempts, we were forced to admit defeat.
Oh.
Around this time, other
That's not
microscopes
good.
emerged that could also image atoms. These probe microscopes work by gliding an incredibly small stylus across the sample. The stylus detects variations in quantum effects or nanoscale forces to then map the surface structure of the sample.
That's cool.
These were easier to build, and because they didn't use any lenses, they weren't limited by spherical aberration. Their images were even 3D.
Oh.
But the looming issue was that these probes weren't really seeing atoms. It was more like feeling atoms.
Throughout the 80s and 90s, this was all we had. But what if there was another way? Scherzer's theorem proved that a diverging radially symmetric lens isn't possible.
But if you're willing to give up on that symmetry, well, the theorem no longer applies. The problem is that radial symmetry is arguably the most important property of any lens, because if you break the symmetry, you also break the image.
But 3 maverick scientists thought there might be a way. Knut Urban, Max Hayter, and Harold Rose were known in the electron microscope community as troublemakers. And for years, barely anyone had been interested in their research. Or more importantly, in funding it.
And for a good reason, too. Their idea was kind of crazy. I mean, they purposely wanted to break the image using a lens that wasn't symmetric. Their hope was that there would be a small part of this distorted image that would be slightly diverging. And maybe, just maybe, this small part could correct the spherical aberration of the original lens. So they got to work.
To distort the image, they used a massive nest of electromagnets with 6,
That
8,
is
or even
huge.
10 separate coils and magnets with bumpy magnetic fields. These were known as the hexapole, octapole, and decapole magnets. So as the electron beam passed through a hexapole, it would twist and squeeze the flat 2D image into a triangular saddle. And the circumference of the original beam would be pushed into the 3 corners, with the rest of the interior stretched out. But now, the middle of the image would have a slight concave bow, giving the effect of a small divergence. Then Rose, Hayter, and Urban forced the beam through a second hexapole, one that worked the opposite way, so it would unbend the distorted image back into a circular shape. But now they calculated this new image might have the remnants of that tiny divergence still in its center, with spherical aberration pointing in the opposite way. So if they got their maths and engineering exactly right, they could feed an image with spherical aberration through these 2 lenses to almost completely counteract the effect.
And I imagine a lot of people in the field.
The animation is really good.
Proposed, right?
Not only the concept, but that this is like technical feasible, I believe. It was thought that this is not possible.
By May 1997, the group had just 2 months of development time left before their last sponsor withdrew their backing. And to make matters worse, their latest lens iteration was still just on the drawing board. But somehow, by the 23rd of July, just a week before their funding ran out, the new lens was ready to test. They gingerly placed it into the microscope, but like every time before it, the lens was unstable and failed. So they decided to switch off the equipment for 24 hours to allow the magnets to settle. And then at 2 a.m. on the 24th, they turned it on again.
Boom!
And almost magically, the picture started to stabilize. Suddenly, there was no aberration. Only beautiful, clear images of Adam.
That reaction over there would be, crazy. They'll be like, golly.
After more than 60 years of failed attempts, Urban, Rose, and Hayter pulled off the seemingly impossible.
Crazy.
With this method, they cut the resolution of the TEM down to only 0.13 nanometers. An average TEM image went from looking like this to this.
I mean, way cleaner, Way cleaner, a little bit more sharp,
like this
way sharper.
To this.
But still...
A few months after the group's breakthrough,
some
Knut
work.
Urban attended a microscopy conference to share these results. But because of the group's reputation, he was relegated to a small back room that barely anyone noticed.
Why every time I see, whenever in these, these old philosopher or scientist or, all these guys used to do something, someone would just come and, would take away whatever, the work they would have done and, not give them all the credits they deserve. I don't know, many videos I have seen, and at the end it will be like, oh, this happened and someone other took his papers and got a Nobel Prize for him and people went crazy for him instead of the other guy. I don't know, but yeah, same thing happening to this guy too. He went there and the guy was like, bruh, go back room, go somewhere else. We don't even care about you.
He was relegated to a small back room that barely anyone noticed. Soon, however, word spread that against all odds, his pictures seemed real. Then a crowd of hundreds formed. People were lining up outside, hoping to get a glimpse of their stunningly sharp images.
Damn.
So we're gonna get a sample holder.
Yes, now we get a sample holder out. We put that under the optical microscope. So the sample itself is a small lamella that you can't see without the optical microscope. Yeah,
Okay.
have a look through that.
Beautiful. On
Okay.
top of the B, there's a prong.
Yeah. And on the very top of that, on the left-hand side, looks like a little bit of dust. That's our actual sample.
I see.
Okay, now I simply go up with the magnification and I do a very few, like more basic alignments. In this electron microscope, because it's called transmission electron microscope, the electrons always transmit the sample. Here we look through our entire sample at the same time. And that's why it's so important that we align the sample. If you imagine atoms in a high symmetry direction are lined up like pearls on a string, when we look down it, well, we can see an image. But if we're in like some random direction, then everything will be just blurred. So that's why we have to do some tilting in the end. And this is where the actual sample starts, the strontium titanate. And this is the thin region where we hope to get atomic resolution.
So this is 5,000 times?
Yes.
Wow.
And we see strontium, titanium, we see oxygen, we see carbon. That's contamination. So most likely what we're looking at here is
Bro,
carbon
that is so clear, dude. So clear, damn.
contamination.
When you do this focus, what are you really looking for?
I look for this edge to become sharp.
Ah. You took screenshot or what?
See atoms.
What?
Wow. That is so clear, dude. Wow.
Just like that.
So clear.
That's wild.
Each and every
Shortly
atom,
after
bro.
the group successfully corrected the aberrations in the TEM, Andrei Krivanik independently achieved the same for Kru's version of the microscope, the scanning TEM. And in 2020, all four were awarded the prestigious Kavli Prize in Nanoscience for accomplishing what so
2020. So it's not that old when they got this prize, huh? Just 5 years ago. And look at all of them, bro. All of them got so old, but you know, they deserve it,
many
dude.
others thought impossible.
That is
Through
amazing.
their persistence and ingenuity, seeing atoms like this is, well, normal.
How big of a difference does aberration correction make?
If you want to see atoms, and if you want to, for example, measure interatomic distances, and if you want to learn what type of atoms you have, you need aberration correction. Any research that's material science, materials engineering, chemical engineering, you need to see what's happening at the atomic level, because
Are they atoms? Yeah, these are atoms. This is what, like, each and every dot is an atom.
you want to relate the properties to the structure. If you can't see the structure at the atomic level, you only have half of the information. So that was a game changer. That's why nowadays every university in principle needs a microscope like that.
Yeah, but I feel like every university cannot afford it too. You get what I mean? But bro, but honestly, not gonna lie, microscopes are really hella interesting, man. You know, like of course I have used them before. They're really interesting. Like sometimes you have to really control and everything, and you know, you have to be really precise on the point to really see what you are trying to see through the microscope. But yeah, W's to these guys, man, who never gave up for what, 60 years or something like that, dude. And look at all of them, like they are so old now, man. But yeah, W video from Veritasium, man, killed it. And now we can see atoms. If you put different materials, different things, I think so, then every atom will have different shape. But in this case, they put kind of a sample, kind of same thing, but still there was something different. The guy said like they can see oxygen and different, you know, elements. But still, I'm not sure, man. But according to looking here now, like, I mean, it's all what you see. Look, all of them look exactly the same. But yeah, but still, man, W's to these all of these guys, especially these 4 guys who came, yeah, these 4 guys who worked as a crew, you know, and yeah, made it possible for us to see these days what we are trying to see under those big microscope, bro. And I know, bro, those microscope gotta be hella expensive, man. But yeah, W video from veritasium, bro.